we shall talk about eccentricity. We spoke about eccentricity maybe 3 videos ago, or maybe 3 or 4 videos ago. This is the eccentricity of an ellipse. And it is computed as C over A, and the value of the eccentricity of an ellipse is somewhere between 0 and 1. So what information does the eccentricity of an ellipse give us? Well, when it is close to 0, if the value of your eccentricity is close to 0, your ellipse looks somewhat like a perfect circle. And when it is close to 1, your ellipse is flat. It looks like a squashed marshmallow. Okay, so what information do you think would the eccentricity of a hyperbola give us? Any guess? Okay. So the eccentricity of a hyperbola, so we are talking about the eccentricity of a hyperbola now, is computed in the same way as the eccentricity of an ellipse is computed. It's equal to C over A. This is how we can look at it. The value of your E affects the angle between the asymptotes. So last time we spoke about the asymptotes, and the curves of our hyperbola follows the direction of your asymptote. So if the angle between the asymptotes is wide, so that means our hyperbola is also wide. So the eccentricity will give us some measure of the narrowness or width of the hyperbola. So again, let us recall, we shall need C and A to compute for your eccentricity. And so C squared is equal to A squared plus B squared. So this is the relationship or the relation among C, A, and B. So that means C is equal to the square root of A squared plus B squared. So this also means that C is always greater than A. So since C is greater than A, the value of C over A is greater than 1. And we can see that from our curve. Okay, so this is the center of our ellipse, and this is your vertex. So the distance of your vertex from the center is what we call A. The distance of your one focus from the center is what you call C. So C over A, because C is greater than A, has to be greater than 1. Okay, so I will show you different curves of a hyperbola and their corresponding eccentricity. So this one is a hyperbola defined by this equation, x squared over 4 minus y squared over 1. Okay, so you have a 1 there is equal to 1. Okay, so what's the value of your eccentricity here? It's C over A. So A here is 2. Okay, A is 2. And then our C is equal to the square root of A squared plus B squared. You have a 1 here. So that's why it's square root of 5. And square root of 5 over 2 is 1.19. Okay, so how about this one? Okay, so this one is a hyperbola defined by this equation. So this time, our B or B squared is less than 1. Okay. Our B squared is less than 1. Our B here is 0.5. Okay, so let us see what's going to happen with our eccentricity. Well, eccentricity is equal to the square root of A squared. Okay, that's 4 plus B squared. This is equal to 0.25. So computing for E is equal to 1.03. How about this one? So this is a hyperbola whose eccentricity is equal to 1.001. Okay, so look at the trend here. Look at the pattern here. As the value of our E gets closer to 1, okay, so what's happening with our hyperbola? Okay, the focal width of our hyperbola gets smaller and smaller. It's like our hyperbola becomes narrower. So that is one interpretation of your eccentricity for a hyperbola. It is telling you the narrowness or the wideness of the branches of your hyperbola. How about when the value of E increases? So in the previous slide, we showed the sketch of the hyperbola when e gets close to 1. But what about when e gets further away from 1? Okay, so again, this one has an eccentricity which is equal to 1.19. Okay, look at that. Okay, so computing for e is equal to the square root of a squared, okay, that's 4, plus b squared. So that's going to be 9 plus 4, that's 13. So e is square root of 13 over 2, which is 1.8. Okay, so look at this. From 1.19, this is your curve, to 1.8, this is now our new hyperbola. Well, let us exaggerate it a bit. What if our equation is somewhat like this? Look at our curve. So the value of your e here is square root of 4 plus 60, that's 20, divided by 2, that's 2.23. So our eccentricity is 2.23. So the further our eccentricity moves away from 1, our hyperbola becomes wide. And you can imagine what's going to happen when our e becomes really becomes a big number. This hyperbola would look like 2 straight lines. Okay? I wonder why that is not included in our degenerate cases. I wonder why. Okay, so our degenerate case for a hyperbola is 2 intersecting lines. But you know, when the eccentricity of our hyperbola is so big, okay, it goes to infinity, what you will see here is a hyperbola that is so wide. When you look at it, it looks like 2 parallel lines. So we can look at the eccentricity as a measure that is correlated with the focal width. Okay, so the focal width is giving you information about the width or the narrowness of your hyperbola as measured from the focus. So again, let us bring back our measurements. Let us bring back how e is computed. It is equal to c over a. C is equal to the square root of a squared plus b squared, and it is always greater than 1. As e approaches infinity, the focal width increases, and so our hyperbola becomes wider. As e gets closer to 1, the focal width decreases, and so our hyperbola becomes narrower. Okay, so something like this can happen. As our e becomes larger, all right, the focal width of our hyperbola becomes larger. It becomes wider. Now, we can also look at the eccentricity as a measure that is correlated to the angle between the asymptotes. So, as e approaches infinity, the angle between the asymptotes increases, and so the hyperbola becomes wider. As e approaches 1, the angle between the asymptotes decreases, and so the hyperbola becomes narrower. So as e approaches infinity, the angle between the asymptotes becomes larger, and so our hyperbola becomes wider.